So I'm going to go over week 1 review. For this first question, it shows you a PES, and it asks you, element X is most likely to form which of the following compounds? So if I write out the electron configuration based on this PES, what you'll notice is that the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So it's actually calcium. It's an alkaline earth metal, which means when it forms a compound, it's going to form XO and XCl2 because its charge is going to be +2. So that's how I got the answer of C. Okay. In 2, it says consider the following redox potentials. Which of the reactions below is most thermodynamically favorable? That's another way of saying which of those has the most positive cell potential. And so what I did for each of these reactions was I had flipped reactions, whatever reactions were necessary in order to get the reactions that you see below. So for A, you keep Au3+, this reaction right here, but then you've got to flip the Br minus, okay? And so you would get positive 0.43. For B, you would flip this Au reaction, okay? But then you wouldn't flip the H2O, okay? And so what you get is negative 2.33 when you add them together. Remember, for cell potentials, you need to flip. If you flip, you're going to multiply your cell potential by -1. But if you have to multiply the entire reaction by a value, you're not going to change your cell potential. So keep that in mind. And so when you do all of them, the one that's the most positive is actually D, which gives you positive 1.90, which is your answer. In 3, it says when the kinetics of the reaction are studied using the method of initial rates, the following data is obtained. So what I notice is that going from trial 1 to trial 2, my concentrations double while my rates quadruple. Therefore, this is going to be second order, so the rate law is going to be K times HI squared. Okay? For 4, the reaction AB is 0 order when the initial concentration of A is 0.25. The initial rate is 0.40. When the initial rate is 0.750, what would the rate be? Well, since it's 0 order, what that tells you is that the concentration does not affect the rate. Therefore, the rate will stay 0.40 molar per second. Okay? In 5, it gives you this mechanism. Notice the first step is fast, the second one is slow, and it wants to know the rate law. So I'm going to use the slow step. So rate equals K times the concentration of N2O2 times the concentration of Br2. But keep in mind, since N2O2 is an intermediate, what that tells you is that you can't keep N2O2 in your rate law. Therefore, since the first reaction is in dynamic equilibrium, meaning the rate of the forward and the reverse are equal, I can write the second step, which I wrote, which was K times NO squared equals K times N2O2. I can then replace the concentration of N2O2 with NO squared, and that gets me the rate law A. Now, if they ask me to explain this, you guys are perfectly capable of explaining this just the way that I explained it, but what you can do, since a lot of people struggle with actually explaining it, what you can do is write out these steps and then explain what you're doing as you go along. So saying, write out the rate law for this rate determining step. Then, since an intermediate is included in that first step, replace it by first finding the rate law for the reaction that's in equilibrium, substitute in NO squared, and there you've got your rate law. Okay? In 6, it says, which of the following salts is expected to have the highest pH, meaning the most basic? So if I look at each of these, remember, you have to determine where each of these salts came from. So NaClO4. Na came from NaOH, which is a strong base, therefore it's not going to be acidic. ClO4 minus came from HClO4, perchloric acid, which is one of your strong acids. So that's not going to be basic, therefore this is going to be neutral. KBr, K came from a strong base, KOH. Br minus came from HBr, which is a strong acid, so again this will be neutral. MgI2, again, is going to be neutral. This came from a strong base, this came from a strong acid. So for D, D is the only option. CaOH2 is a strong base, so this isn't going to, calcium is not going to be acidic, but Cn came from HCN, which is a weak acid, which means that the CN minus is going to act as a base. So D is your answer. I'm going to go through this free response question. This came directly from an AP. For A, it says write the equilibrium constant expression. So remember, it's products over reactants. And I actually wrote it as Ka. You could have just written K, that's fine. But since I know this is a dissociation of an acid, I know this is going to be Ka. Ka equals the concentration of C3H5O2 minus times the concentration of H plus all over the concentration of the propanoic acid. In B, it says calculate the pH of a 0.265 molar solution. Okay, so I'm going to set this up. I start with just 0.265 molar of my acid. I don't have any of the conjugate base or H plus. Because it's a weak acid, it's going to change by X, so it's going to be minus X plus X plus X. So I get my equilibrium concentrations. I set this up with my Ka value. I get rid of my X, making sure to show my rule of 100. And when I solve for X, I get 0.00188 molar. But it's not asking for the concentration of H plus. It's asking for the pH. So I'm going to take the negative log of X. So I get 2.725 because I want 3 significant figures. So I want 3 decimal places for the pH. In CI, it says a 0.496 gram sample of sodium propanoate is added to this solution. Assuming that no change occurs, calculate each of the following. So by adding the sodium propanoate, what I'm actually doing is instead of having this value being 0, there's going to be an initial concentration of this conjugate base. So the first thing an I asked me to do is to determine its concentration. So I'm going to take its mass, divide by its molar mass in order to get into moles, and then once I get the moles, I'm going to divide by the volume, which is the 50 mils or 0.05 liters, because it said the volume did not change, and I get a concentration of 0.103 molar. So that's for I. You definitely should have gotten that one. In II, okay, now it says what is determine the concentration of H plus. So it's just like what I did in B, except now I have an initial concentration of my C3H5O2 minus, which is what I calculated in CI. So I've got initial values for those. My change is still going to be X, so minus X plus X plus X. Since this is still 0, that's how I know this needs to be plus. Okay. Then when I set up my equilibrium expression, I can get rid of these X's, assuming the rule of 100. And so what I get when I solve for X is 3.45 times 10 to the negative 5th molar. So I got rid of the X's that I was adding and subtracting, but I kept this main X right here. Okay, so that's my answer for II. I got my concentration. Then it gives me a whole new ion, HCO2 minus, and it tells me it reacts with water to form methanoic acid. So this is the base, which then becomes the acid. Okay, given that the concentration of OH minus is 4.18 times 10 to the negative 6, in a 0.309 molar solution of sodium methanoate, calculate each of the following. So this wording is a little bit tricky. It tells me my concentration of OH minus. What it is saying is that that's the concentration of OH minus at equilibrium. Meaning, if the concentration of HCO2 minus is 0.309 at equilibrium, the concentration of OH minus is going to be 4.18 times 10 to the negative 6. Because I only started with this base, therefore my concentration of OH minus would be 0. So when I was doing this problem, I anticipated some people accidentally putting the 4.18 here. Whenever they're giving you the concentration of OH minus, they're most likely, unless you're reacting an acid and a base together, if it's just a base dissociating or just an acid dissociating, what they're doing is they're telling you, hey, at equilibrium, this base produces this much OH minus. So that'll actually end up being your X when you're solving this, will be the 4.18 times 10 to the negative 6. Therefore, when I'm solving for Kb, right, remember Kb is going to be the concentration of this acid times the concentration of OH minus divided by the concentration of HCO2 minus. So when I solve that, I get 5.65 times 10 to the negative 11th. To solve for Ka, I just need to take 10 to the negative 14th and divide it by 5.65 times 10 to the negative 11th. And that'll give me my Ka value, which I got here, 1.77 times 10 to the negative 4th. Do be careful because this Ka times Kb equals 10 to the negative 14th is true only when you're at 25 degrees Celsius. So they didn't actually clearly stipulate that they are at 25 degrees Celsius. They should have. If it isn't clear, then you can assume this. But do be careful because sometimes that might not be true if you're not at 25 degrees Celsius. In E, it says which acid is stronger. Well, the one that's stronger is going to be the one with a higher Ka value. So for the propanoic acid, its Ka value is 1.34 times 10 to the negative 5th. For methanoic acid, it's 1.77 times 10 to the negative 4th, which is larger, which means methanoic acid is a stronger acid since it has a larger Ka value, and that's how you would explain it.